Hello, this is the Phase F Hydration Monitoring Wristband, and this capstone is composed by Fabiola Pons, Gabriela Lugo, Jose Martinez, and the Professor Alex Peles.
Hello. The outline for the Phase F presentation, we're going to start with the system validation, which include the manufacturer system, the manufacturer process, the verification or validation results. Then we're going to talk about the overall project conclusions and finally the project recommendations.
Now we have the manufacture process. Sweat sensor detects hydration levels via sweat composition. Microcontroller processes data and controls the system. Compact battery ensures consistent portable power. Display shows real-time hydration feedback. Ergonomic wristband designed for comfortable and continuous wear. Assembling use precise soldering and encapsulation to protect components. And we can see the following images. That are provided only for visual examples as a potential of the prototype. We see the wristband, the display, the sensor, and the full hydration monitoring wristband. Audio.
Okay, here we have the verification or validation results. As we mentioned before in the Phase D presentation, we use three methods for the verifications. The first one is the system simulation via modeling tools, where we simulated sweat data using a Python code, the one that we have here on the right. For that, this code help us to create synthetic datasets that represent the sweat potassium levels. We use two conditions for the datasets. The hydrated state used with levels between 3.5 millimolars and 5.0 millimolars, and the dehydrated state with levels above the 5.0 millimolars. To the code, we added randomized noises to mimic the sensor fluctuation, and some specifications. We generate 100 total data points where 60% of them were hydrated range and the other 40% were in the dehydrated range. As I mentioned before, the Python code for generating the sweat data is the one at the right. Here we have the data set. We classify it between dehydrated or hydrated, and we put it on an Excel sheet. The summary for these methods, for the results, are the verification goals where the simulated sensor input behave as expected. The alerts trigger accurately at threshold. The alert system responds with the time requirement, and the dataset realism was verified. And here we have another summary for the methods used that I explained before. The second method used was the component datasheet analysis and compatibility testing. For this, we used three datasheets, the one for the sensor, the one for the microcontroller, and the one for the LiPo battery. And the results, we can say that the verification goals were the electrical compatibility of all components, where the method was voltage and interface matching confirmed via datasheet review. The sensor and microcontroller response time meets real-time needs, and the method for that was the combined input to alert delay, and the power consumption suitable for daily operation, where the method was to active draw 17 milliampere and 150 milliampere battery supports for 24 hours runtime with sleep mode. The third method used was the benchmarking against similar systems. We compare our design with three similar designs that are on the market right now. The three different devices that we compare were the Gatorade GX Sweat Patch, the EpiCore biosystem wearables, and the equine system electrochemical sensors. Here we have the 3 data sheets for each one of them. The summary for the results were that the verification goals performance comparable to commercial system, where the method used was simulated system, and the detection accuracy and timing was reasonable, with a 90% correct dehydration alert across test cases, and the threshold logic aligns with literature, where the method used was 5.0 millimolars potassium threshold, matches the published physiological dehydration markers. Again, here we have the summary overall for all system level Ps. The first MOP was the hydration status determination accuracy. The method used was simulation, and the result we achieved 92% accuracy compared to the reference hydration measurements. The second MOP was the latency of alert. We verified through simulation. The third MOP was the voltage and current compliance. The method for verifying this MOP was the analysis and inspection, and the result were the power draw and supply voltage met the microcontroller and sensor specifications. The fourth MOP was the sensor output compatibility with the microcontroller input, where the method that we used was the inspection and simulation. The fifth MOP was the power consumption, allowed 24 hours operation. We conclude these results through the analysis method. The sixth MOP was the performance with the 5 to 10% benchmark system. Again, we use analysis and simulation to verify this MOP. The seventh MOP was the 50% feature functionality match with competitors. We analyzed the different competitors that we mentioned before. And the eighth MOP was the system calibration eighth, with the method used was analysis and simulation. Now Jose is going to talk about the overall project conclusions.
Thank you, Fayla. Now we have the project conclusions. As all the measures of performance were successfully met, as Fayla mentioned earlier, the validation was done via simulation, datasheet analysis, and benchmarking. As we have no physical prototype of the device, the detection accuracy was 92% using sweat ions, and the response time was less than or equal to 1.4 seconds. The power efficiency was over 24 hours of continuous use, surpassing or achieving the MOPs of greater than 24 hours of continuous use without recharging it. The component compatibility was confirmed, and ergonomic designs ensures comfort and continuous wear for users, and the protection of electronics shielded from external damage. As the conclusion, the project meets the design and performance goals.
Now we have the overall project recommendations. We have sensor integration, add sodium and chlorine ions, selective sensors for comprehensive electrolyte monitoring. We have the data accuracy, use real samples from a diverse population to calibrate sensors and account for individuals' variability. The prototype development, build and test a full wristband, not just a simulation, to validate real-world functionality. And then the system testing, evaluate sensors, microcontroller integration, system latency, and actual power consumption. Design improvements, miniaturize components and enhance ergonomics for better wearability. Power optimization, implement energy-saving techniques, duty cycling, low power modes, or energy harvesting. Mobile app enhancement, add hydration trends analysis, personalized feedbacks, and cloud syncs for long-term health tracking. And then clinical and field trials, collaborate with healthcare, sports, industry professionals for users, trials, and validation. And then scalability and manufacturing, explore cost-effective materials, and scalable production methods for market readiness. That will be all for our capstone number 2, the phase F. Thank you.